Good morning.
Hey Drew, how goes it?
Good, good. Pretty good. Hey, wow, it's good to see you, Reza.
It's been a while.
Yeah. So, no, there's a little scramble when I first join because I usually use Teams, Microsoft and all, but every which conference systems, it picks a random speaker of my microphone combination. So, like frantically clicking to get back on the right thing. But yeah, it's great to hear from you. Wow, me, Antonio and Reza. Wow.
Hi, Drew. How are you?
Pretty good. It's awesome to hear from you.
It's good to see you. Good to see
Yeah,
you.
yeah, likewise. So, we'll give people a moment to join. Yogesh is out, so you're stuck with me. But so I've got a couple of I've got we'll go when people join we'll give folks an update on where we are with the doc with some good news because I think we're pretty close to having it approved and and then what I want to do is think about next steps a little bit. Um, and part of what I've been doing, and I've had a lot of help from folks like Charlie and others, is uh, is trying to um, generally raise the level of understanding of how things work when things are failing and how failures occur. And the thing that I see happening with memory over and over again is people try to count the number of memory errors and base their actions off of that. And like I can't tell you how many times Roy has told me don't do that, and I agree with him. So one of the things that I've written up is an area for um, just like a memory error, and how does a memory error grow into a problem? And and I was doing that with the intent of illustrating some of the problems with counting. So uh, if that's okay with you all, what I thought we would do is we would um, we would talk a little bit about the status of the document that we're about to publish. We would look at the memory scenario a little bit, and then in the coming meeting we can figure out what comes after the scenario. But if it's okay with you, I don't think the scenario is going to take very long, and if we can get it to the point where it's ready to also publish as a contribution somehow, then we can point uh, our friends to it and other companies that are a little confused about how memory works. So hopefully that makes sense to you all.
Yep, that works for me.
Awesome. Okay, so with the document, I have I'm not as good at this stuff. I'm not a paperwork person. I'd rather just put my hands on the keyboard and write. But I've been pushing it through the process, and we are scheduled for August 19th at the hardware management meeting to have a review. And the reason we do that is the hardware management team is our parent project. So they approve the contribution, and I will go through some step that will turn it into a PDF somehow. I've given them a PDF. I think what will happen is they approve it, and if they approve it as is, then it'll show up as a contribution on the OCP website. So at that point, we'll be official. We'll have published it, and that will be awesome. That'll be a landmark that we've got this published. And just so folks are clear, I'll put a link to the doc in the chat. But what the doc says is what we want to log for DDR5. So there's the DDR5 paper, and I don't know, any questions or comments before we move on to the next thing? Okay. And Evan, I see you joined. I don't know if you heard. we're up on the 19th to review with the hardware management steering committee. So
Okay.
good news. I mean, you know, I don't. They're not going to tell us we don't know anything about memory. So you know, they may have some comments on the format of the paper or something, but you know, we'll see.
Yeah, that's fair.
So the paper is being published as a kind of a white paper. It's not an official, we're not calling it a specification. We're calling, because it's a requirements document. So requirements document, white paper, that kind of thing. They don't require CLAs because they're requirements. They don't have, they're not supposed to be something that has IP in it. So, so that'll streamline things. If we ever do decide to publish a specification, then we'll have to have contributor license agreements signed by everyone. And that's not to make this group exclusive. Well, I think we really want to keep it open. It's just to protect the spec so that if we put something out there, no one can come back and say, hold on, I didn't mean to put that in the spec, and make that public. But anyway, so with that, if there are no questions, I'll pull up the scenario doc. And is that okay with people if we talk about the scenario this, you know, for like it shouldn't take long, like a week or two, and then we'll start working on, you know, whether we dig into you know, LPDDR or HBM or whatever.
That sounds great to me, Drew.
Sure.
Cool. Okay, I'll start sharing. And actually, before I share, let me grab the link to this doc. And so one of the things that we've done in the fault management team is what we realized is that walking through the scenarios was extremely valuable, but it was holding up our documents. And so it was really slowing us down. And so uh, I think it was Mita. Someone suggested let's pull these out and have a separate list of them, and then we can move faster. And so we did that. And the beauty of this is then now we can have focused scenarios that we tie to other scenarios. So we can link this to the poison. You know, we'll have hopefully have a poison scenario at some point. I have my poison doc, and so we'll have a kind of a network of documents that talk about how failures work and how error logging works, and and we'll build up enough reference material that someone could jump into our web of documents and become knowledgeable about fault management. And that's the dream for me, because I feel like if more people understand this, we'd have fewer conflicting requirements to our suppliers, like you all, the memory vendors and chip vendors. And if we got rid of some of those conflicting requirements, then we would we'd be able to, you know, move a whole lot faster and converge on what we want. So I see people requesting. I saw a Gmail pop up. If I will add folks to the document if I see the request. Can you all generally get into this doc? I'm looking at.
No, Drew.
Okay, Theo, I will add you.
Thank you.
Let's see. Oh, okay. I'll review and share. Yeah, and I'll gladly share access. And yeah, Reza, I see you asked as well, and I'm sharing it with you. Okay, and I'll share the doc as I walk through it. So this document is intended to be kind of a progression that says, hey, and there are a couple of things that people generally misunderstand. They misunderstand the nature of corrected memory error. Their assumption is that I get a corrected memory error and I can figure out what it means. And so one of the points of this document is, well, you get a corrected memory error and you know something, you know some bits were flipped and where, but you can't infer the failure from that until you see a pattern of them, and that pattern will reveal whether it's a word line arm or SynSamp or DQ or whatever. But it requires a pattern over time. The other thing that this document's intended to show is that as folks that are trying to diagnose failures, we are along for the ride. What I mean is we are dependent on the access patterns of the software to understand errors. And the patrol scrubber plays a crucial role in giving us a once a day clue that, maybe there's a memory error the OS isn't using. But the number of errors that we get and the rate at which they occur is related to what software is doing on the machine. And so a high error rate could be a single bit error that software just happens to access frequently. So the scenario kind of progresses from an error that exists but maybe no one sees except the patrol scrubber to something severe that where we want to replace a part or do a self-repair. If I'm open to restructuring this. If people want to dive in, Mita's already been in it. I love it, Mita. Yeah, thank you for your comments, and I just haven't gotten to them yet. I've been busy with all the other docs, but yeah, this is great. And I'm also comparing polling and leaky bucket and rate limiting, because one of my concerns is polling works. Leaky bucket bothers me if you rely on the interrupts from leaky bucket, because if I have a very low rate of memory errors, leaky bucket will not fire. And so, but that may be, the low rate of errors may be software isn't using it often. Software could change its mind and start using that memory often. And something that was pretty benign could become severe. And I had early warning in the form of early memory errors, but the leaky bucket hid those. So, and then I'm talking about rate limiting, which is an alternative hardware implementation that just says, give me the first error and then don't give me any more interrupts for a period of time. And I'm going to kind of push through on the quick side for some of the stuff at the beginning, but please give me feedback. And Mita, I'm so sorry I haven't addressed your feedback, but as you know, we've been busy, so I will get to it.
Yeah, no worries.
So, okay, so the following assumptions apply, right? That the memory controller has basically the ability to correct all the errors from a single chip. And I think that we may want to add the bounded fault, because I'm finding that as we talk about applying better ECC to things like LP, we're going to have to talk about bounded fault at some point. So, or maybe it's a different document. I'm very flexible. And then the other assumption is the memory controller has some sort of scrubber, demand scrubber and patrol scrubber. And then I'm talking about DDR5 behavior. So, okay.
I think another thing
So-
worth clarifying up front, and I did have a comment on that, is that we're talking about hardware implementation here. Like rate limiting, for example, can be done in hardware. It can also be done in software. And I'm assuming that for this document, it's all about hardware, right?
It's really about, it's kind of about the system, but I could clarify that, because polling is a software, like what you do with software is you say, like if you have a really high rate of errors, what a lot of folks do is they go, hey, I don't want to deal with this number of interrupts. It's hurting me. I'm just going to ignore the interrupt for a while and poll periodically. So maybe I need to clarify that. But it's really the solution behavior, and yeah, the leaky bucket and rate limiter are implementing in hardware, but it's kind of a contract between the software that's doing the logging and the hardware.
Okay.
So,
Another thing, I think maybe leaky bucket, it would be good to click, because leaky bucket is used for so many things. It's not necessarily only used to hold back reporting of errors. It can sometimes be used to reduce link speeds when there are too many errors. So it would be just good to clarify that that's the kind of leaky bucket being referred to here is to,
yeah.
not surface an error right away.
Yeah, yeah. Well, and I guess I don't, let me think. Yeah, I'll say leaky bucket thresholding or something.
Thresholding for error reporting. right?
Yes, okay. Thank you. That's a good clarification. Thank you. Okay. Theo, it looked like you were going to say something, or was it Charlie?
Yeah, I had a question, Drew. Am I correct? This is more focused on like DDR5 like technology, or is this supposed to be all encompassing for all types of memory?
I think in this example, we're focused on DDR5. Some of the
Okay.
principles apply though, because um, we're always kind of along for the ride, right? It's the errors that we see are dependent on the patrol scrubber, which doesn't report errors that often, or cause errors to be reported that often, and the software behavior patterns. So there'll be some principles that are, pretty universal, but the scenario itself is focused in DDR5.
Yeah, just some subtleties like, when we say all errors from DRAM can be corrected, those kind of assumptions, I think some of those would have to be modified.
Yeah. Well, let me make sure. Okay. So uh, let's see. And so what I'll do is move the DDR5 up to the top front, and that way when you walk through the assumptions, it's the first assumption is DDR5.
Oh, thank you. Yeah, I didn't see that. Thank you.
Okay, it was listed as an assumption, just not up front. So
Okay.
that's a
So-
simple thing.
So, Drew, I have a question on leaky bucket. I've seen it used a little bit differently, or maybe our terminology isn't quite aligned. But the way I've seen leaky bucket used is each time an error occurs, that the correctable error count is incremented, and then when that count hits a certain threshold, the memory is declared bad. It's I don't agree with the methodology, but that's the way I've seen leaky bucket used. So over a certain period of time, a certain number of errors have occurred that meet the counting threshold to declare the memory bad. So
Yeah.
in that scenario, I'm thinking isn't there an interrupt for each correctable error that occurs, and the software does nothing with that interrupt other than count it. And then there is, when the threshold is hit, that's not okay. Let me step back a little bit. I'm assuming when we use interrupt, that's a message coming from the hardware to the software to either take some action or note something has happened.
Just to log the error and log.
Yeah.
So you get the interrupt, you log the error, and then you figure out what the error means and do something about it. Yeah.
Okay. Yeah. So there's kind of two. Then there's the interrupt for each correctable error. The software can be counting that over a window of time, and then if the threshold isn't hit, then it dumps the counts from the prior period of time, say a 24-hour.
It leaks them. Usually it'll just decrement them, or it
Yeah.
might dump them, but it might or decrement them. Yeah.
Yeah, or decrement them, whatever. But in that scenario,
Well, I can address
Okay.
some of what you're thinking. I mean, I think like from what you've said so far. So one of the things that happens is we have this leaky bucket counter in hardware, and so a lot of folks will use it for rate limiting, but it's not a great rate limit because if though that's the only time you pay attention to memory errors, you're losing some because you haven't crossed the threshold. But some people even go further and say, well, when the leaky bucket threshold trips, then I know that memory needs to be replaced. And I
Right.
talked to one high-end scale-up server vendor who tried to tell me that, yeah, they had advanced RAS features because they were using leaky bucket counters to decide memory was bad. And my comment back to them was, you don't really understand how memory fails, and you
Yeah.
don't understand how memory errors work if that's how you decide that memory is bad. Go talk to a memory vendor because I don't think any of the memory vendors would love that idea of just let's count the errors and decide the memory's bad.
That's why OnDie ECC was the
Well, it's one of
vendor's
the
push for
yeah,
that, right?
it sure helps. It sure helps
Yeah.
get rid of the single bit errors that people
Yeah.
were replacing memory for. Yeah.
Right. Okay, so I guess my question is the use of the term on the first sub bullet interrupts when a certain number of errors occur. I'm thinking should maybe a better wording would be takes action when a certain
Well,
number.
how about let's be specific. It triggers an interrupt to logging software when a certain number
Okay,
of
sure.
errors occurs. Okay.
Okay, good. Thanks.
And
it's
then
not really a certain number of errors, right? It's when the rate of incoming errors is that much higher than the rate of outgoing errors because the bucket is leaking away.
well, that's kind of the next bullet. I mean, really, there's a threshold number, and when that number is exceeded, you trips, but it leaks, and so that's kind of the next thing.
Oh.
You see what I'm saying? Like the
Yeah,
the threshold doesn't change. The threshold is fixed. It's just, but I guess how about within a time frame?
So, so Drew, it sounds like, I mean, the very first bullet, polling, that's what software action is, right? Are
Yeah.
your top bullets, the way it's structured, do you want to bifurcate software actions, hardware actions? Because as folks are mentioning, people are used to seeing different behavior from some of the terms that is used here. So we can probably eliminate that confusion if we just talk about the action, right? First bullet is polling, which is what software does, and decides based on what it sees, based on its own implementation. Second bullet seems to be what you're suggesting as hardware proactive notification of the error, if that is what your intent was. So the intent is yeah.
Yeah.
So this is, you are really thinking, here what you're thinking is how hardware can proactively signal a given event. And then underneath that umbrella, there are various methods hardware have adopted to go about that interact.
It's a solution level view. It's how do the hardware and software work together to log
Yeah.
errors.
Yeah,
Perhaps
Reza,
there should be, sorry.
go ahead, Mita.
Yeah, I was just suggesting that perhaps there should be a fourth bullet for software rate limiting, which doesn't quite fall under these three categories right now.
We can look at that as we walk through the scenario. The only thing about software, actually, software can rate limit, but that's effectively what polling does.
Well, it's not exactly polling. It's like adaptively going into interrupt mode and polling mode. Actually, I kind of laid it out in my comment on the right.
Okay, I
yeah.
see. So let's yeah, I will put it here then, and we'll think about it because like the classic thing software does is it does effectively do that because a lot of software will just take every interrupt, and then when the interrupt occurs too fast, we revert to polling, and that's effectively rate limiting because what you're saying is
Yeah.
I don't care how fast the errors occur. I'm going to poll once every 1 minute or whatever, and that's the maximum rate of errors I can get at that point. But the problem with that is it's not pure rate limiting because you took interrupts initially, so I got a burst of fast errors, decided I was in an error storm, and reverted to polling. So that's the only difference. And if you're designing an error handling pipeline, now you have to. It's okay, but you have to. If you design the pipeline, look at queuing theory. You have to design in the ability to handle a surge in errors, and then the errors backing off.
So I like Reza's comment in terms of separating out kind of the hardware, what the hardware is doing versus what the software. And it brings me to my next question is when you say interrupt, is that what the hardware is doing or is that what the software is doing? Because in my mind, when you get a correctable error, the hardware corrects it and writes something to a register. Now, how fast or how often the software reads that is to it, is that the interrupt, or is
Yeah.
the interrupt the hardware writing to the register?
The interrupt is when an error occurs, we latch the error, trigger an interrupt, and usually, and that's another point about memory is I've had countless discussions with people about, hey, we don't want to pull memory errors, we don't want to sample them, we want every single memory error, and I'm like, good, you can attach a logic analyzer to every single one of your systems,
Yeah,
but they
that
can happen at a rate higher than any software can log.
that dog don't hunt.
Yeah. So that's part of kind of where I was coming from with this, is that you get an interrupt that triggers logging, and in the meantime, you might have had another error, and you'll have an overflow bit typically that just says I overflowed, and so and I think like we've talked about overwrite rules and hardware fault management,
Yeah,
and so
yeah.
one thing we may want to do is write up like error overwriting rules overview, a separate scenario, and then reference that here and say, when the interrupt occurs, the hardware has latched an error, and now software is being told about that so it can go read and clear the error. And then until then, the error overwrite rules may prevent us from logging another error depending on the implementation.
Sure. And I think that would be a good separate knowledge article to
Yeah.
go into more of those details. So I guess my question is, are you defining interrupt as a combination of the hardware writing to the error registers and then the software reading that? So it's kind of it's a two-step process.
So perhaps instead of interrupt, we should just use the term we agreed on in the earlier, is like error signaling, and that should.
Okay.
I mean,
How
does that?
about error interrupt signals logging firmware when a certain, I want to use the word interrupt because it is literally an interrupt, right? Interrupt is, if I go to an OS person and say, if I say you're getting a signal, they're like, what? Because a signal means something else in Unix.
Yeah, I
Like
agree.
good pill.
Yeah.
So I can say interrupt signals logging software.
Yeah. So only one comment I had on that one, maybe an explanation, Drew, is you mentioned within a time frame. Typically, the interrupt is unaware of a time frame, right? The leaking is periodic, so it has some knowledge of time. Do you agree with that?
Yes. Yeah. So I mean, you've got to, and that's what I was trying to say originally, is it's really the way it works is you have a trigger that interrupts when a certain number of errors occur, but the number of errors gets decremented periodically so that and the effect is that you have to have a rate. So I can work on this.
What
Definitely.
Okay.
is your primary feature of interest? Is the fact that corrected error is being thresholded, or is the primary feature of interest is the fact that errors are being leaked so that kind of addresses the very last bullet, handles error storm, which it all depends, right?
It's just what we're looking at here is like how do all of these work in conjunction with software accesses to trigger a stream of errors to us, and then how do we make sense of that stream of errors? So if you look at the scenario, I talk about there's like a part of a row on memory fails, but it's not allocated. So now this is the fault, but the patrol scrubber sees it periodically, and then the software starts using it, and maybe, or maybe there are no errors. Actually, they begin with no errors because I have a stuck at row, but it's stuck at 0 and I've written all zeros, so there's no error. The patrol scrubber sees nothing. Now someone writes a 1 somewhere but doesn't read it back. Now the patrol scrubber sees an error once a day. So what I'm trying to show is that we need to think about what software is doing, because we're not directly testing memory, we are counting on software to write something that memory can't store correctly. And then when we see the error that results from that, we have to collect those in a correct way and then process those in a correct way to infer the fault. So it's not just about thresholding. In fact, it's really not about thresholding. But I'm showing that the interrupts are, like the way you gather your error data matters, because you can blind yourself to things if you gather it in a poorly chosen way.
So, Drew, another question. This is a great discussion, but it now occurs to me that there are different levels or different pieces of software. So one piece of software is somehow capturing the error when it occurs from reading the error register and incrementing. Is there another piece of software that then looks at what that incrementing, the software that's doing the incrementing, and when it hits the threshold, then makes a decision?
Well, I don't want to. So the way I would describe it is, we have error collection. If you think about the hardware fault management document, we have CPER error logs, and then we have analyzers, and that's what we've been talking about in FMFM. And so the analyzer is going to get time series error logs. That's our goal, and from that time series, it will discover the pattern. And so, what we're talking about is, how do we log that time series? And that's a really good point. Maybe I'm going to put a reference to the FMFM doc, and just a reminder, uh, and a reminder of the structure. We're talking about, we collect errors, we process those errors and come to some conclusion. So there's a fault that occurs, and maybe the fault triggers errors, maybe it doesn't. You can have faults that don't trigger errors, like if you're stuck at 0 and you wrote a 0,
right?
No error, right? And so that's what I'm trying to walk through. Is you have a fault, then you may or may not get an error from that fault, and you may not get an error storm from that fault, and that fault may or may not be something that's urgent to repair.
Right. Yeah. Because it occurs to me that from your description, you could have two leaky buckets. One leaky bucket for the runtime errors, which catches these CE storms. Another leaky bucket for your patrol scrub that might say, hey, over a 48-hour period, if I see the same error occurring 3 times, I know that's a stuck at.
But see, I don't want leaky buckets kind of broken. I don't want leaky bucket. What I want is, like the leaky bucket I'm talking about is not analysis, and the analysis could be very memory vendor specific. But the memory vendor may say, hey, if I see errors along a row ever, I know of a flaky row. Or they may say, well, I want to see errors along a row in the last 90 days. But that's not the scope of the document. The scope of the document is, you need to look for a pattern along a row. And you need to have what we want to see is, we want to see. Gosh. Bucket in this context. My phone thought I was talking to Google. Okay, so the point here is that you've got to collect a stream of data, and we want the early errors, because that gives us more time to look for the pattern, especially when the pattern is controlled by what software does, and we don't control what software does.
Right, aside from the scrubber, the patrol scrub.
Yeah, I mean, the patrol scrub is hardware generally. It's a hardware state machine that we don't control. Well, I mean, we just tell it go through.
Turn it on or off.
and maybe in an advanced scenario, we could have something that says, I think this memory is a little flaky. Let's go redirect the patrol scrubber to take a look at this thing. And like, that could be what happens with this infrastructure. And that's one of the coolest things about the fault management infrastructure, is that I could send a CPAD back to the machine that says, hey, let's do a targeted patrol scrub of a certain range of addresses, and maybe even a certain stride. And what I mean by stride is, if you've interleaved memory across ranks, then there's presumably some distance between ranks that would hit a particular memory. So you could send a message back to the patrol scrubber and say, I want you to to take a look at this region of memory on this particular DRAM. And in my dreams, we would have a feature that would store the row um, and allow us to read and write patterns to the row to find stuck bits, and then write the original row back, all while hiding the fact that that row is being changed from the customer, you know, the end user. And we're not doing anything nefarious, right? We're just looking for bad bits. And you can't do that if you can't write to the memory. So if we could have a memory test that would walk through memory, even if it was slow, um, we could send a CPAD back to say, here's the test I want you to run, and and we can go really figure out what's going on in memory. That would be like, you know, like I think what we're going to do here is going to make a pretty big jump in terms of accurate memory diagnosis, but I think being able to have a more advanced scrub where we can actually write something to memory would be like a 10x jump in our ability to diagnose memory errors.
Yeah, it sounds a little bit like post-package repair, where you would kind of focus on a particular piece of memory that you were going to repair, so you would have to move all the data out of that.
Yeah,
But
exactly.
so for the scrubber, you would have to move all the data out and let the scrubber take over that piece of memory. But yeah,
Yeah, so that's the kind of thing we can do with CPADs. And you know, one of the things we've been talking about with CPADs is you could even send something that looks and smells a whole lot like ACPI bytecode. You know, so let's say I was doing a post-package repair, but I don't like the way my post-package repair is working in the microcontroller or whatever, you know, is acting in the RAS API endpoint. If I don't like it, I could send a CPAD to that endpoint that gave it a series of instructions to follow, you know, kind of like that bytecode. And it's an alternative way to trigger the post-package repair that alters the flow that was built into the microcontroller. It's different, and it fixes whatever problem we found. The same thing could be used to potentially test memory if you have a way to buffer some, you know, small amount of memory. So anyway, but that's like the pie in the sky. That's like a glimpse
yeah,
into the distant future, right?
yeah.
But that's the intent. So and the key is that we need to gather the data and get representative data across the entire period of the fault, you know, as best we can, to give the analyzers the best chance at recognizing not necessarily a count, but a pattern. And what I mean, the reason I say that is because I might see one error in every column address for a row, and that might be enough to convince me I don't need two errors in every, you know, I may not need two errors in every column address in the row. I may need, you know, three different columns in a row telling me that I've got an error on that row, and then we map it to a subword line or main word line or something and say, okay, let's trigger the post-package repair. And the way you think of it is you look at the pattern long enough to develop confidence that you understand the fault. And when you reach a certain level of confidence, then you send a CPAD saying, and you can say that in the CPAD, you can say, I've seen two errors on the row. I'm like 10% sure you should do a post-package repair. Or now I've seen, you know, 30 errors, different errors on a row. I'm pretty sure I've got a problem on this row. Go do the post-package repair. And maybe the confidence is now 80% or 90%. Or you might do something really sophisticated and use machine learning or artificial intelligence. And we did this at Google when I was there. We were, you know, doing things with AI to look at faults, and it would find stuff. You know, it was pretty interesting. And so I think that you know, we might do that. It might not be a pure threshold. So it might be AI somehow recognizes a pattern that's been trained to recognize and says, nope, you're in danger, go do something. So that's why you hear me always back away from just a pure threshold.
Yeah, I think Pat, you're right. Pattern is more important than
Yeah.
threshold.
And I don't know if it's a count or if it's a pattern, you know, like I don't know. And I don't care. What I care is that the memory vendors figure it out and it's accurate.
Yeah.
All right. And it may be different for every memory vendor, and we've accommodated
Absolutely.
that.
Yeah, as the memory architecture changes, the patterns
Exactly.
change also, but that's what the DRAM vendors will know. They'll know the different failure modes and they'll know the patterns that go along with those modes.
Yes.
And
And
you know,
DRAM vendors, I hope we're not stepping on your toes. You know, but I hope this shows that we've been listening to you.
It very much does, at least
Yeah.
for Micron side group.
Cool.
I was just gonna say pattern is hugely more important than count.
Cool. Okay. Thank you. Okay. So, you know, why don't we, so here's my proposal is we're running a little short on time. Maybe what I'll do is I'll give you an overview of the scenario and then we can come back to all these things. But let me give you a quick overview, and then I really encourage folks to get in here and propose changes and you know do some editing. You know, Evan, I mean, I started this, but I would love to have other people's names here. So I take the blame for it right now. But if you know you all want to help us, think of this as a tutorial that we agree upon and publish that we can point all of our customers and partners to get them aligned on how things work. And if it's useful, if you think it's useful, please contribute. Um, so you know, one of the things I wanted to address is misconceptions. Like identify, yeah, there are people like, hey, you got an error, and a lot of folks are tempted to map a single error to a fault. And with memory in particular, you do not know from a single error what's failed. You really just don't. There's so many failure modes that affect more than a single memory address that just doesn't make any sense. And so I want to kind of say, hey, no, you've got to look for a bigger pattern. And then the ability to diagnose memory solely by counting errors. You know, I can have a single stuck cell that generates an error at whatever rate you want, because software may just be accessing a particular cache line at whatever rate. I mean, it needs to, but it could be really fast, and that could drive just about any counter and cross it. But maybe if it's a single bit error, it's not a problem with chip kill ECC. And then the
Okay.
other thing is then, oh, please go ahead.
I'm sorry. How about that workload dependency on the error count? Because when you see the error logs, always it is dependent on the accessing pattern. So, for example,
Yeah.
the demand read operation is more specific area of the DRAM device is continuously accessed again and again. That means the error log count or error counts increases. So when we see the DRAM fault, the error rather than the error counting, but the error distribution is more important. In that terms, the Petrus curve plays the crucial role. So, and in terms of the kit error counting threshold, that is so dependent on the demand read error pattern. So how about to separate those two things? The demand read the error counting requires the regular address striding method, such as the Petrus scrubbing. In that case, the variable error count or threshold value is we can get.
Well, and I guess what I'm saying is it's a misconception. So I'll make that clear. You know, like this is a mistake, right? And so I agree with everything you said, but I guess hopefully it's clear that I'm not saying you can count errors. You know, that maybe that'll make it clear. But I guess so. Do I need to add something? Like, is there a misconception? Like maybe one of the misconceptions is that the control scrubber is not important or something. I'm not. I mean, I hear what you're saying, and I agree with everything you said, but I'm not sure what to add. So if you can help me figure out what to add, I'll.
Okay, I will add the comments on this document.
Okay, yeah, yeah. If you show me like, and if we want to add misconceptions, you all talk to more customers than I do. So if there are common misunderstandings that your customers have, and you want to address them here, feel free to add a section, and and we'll do that because I think you and I know we've talked enough. I believe you and agree with you. So uh, let's do it.
Okay.
That's great. And and
Uh,
the
yeah.
Oh, sorry, go ahead.
No, no. Actually, recently we submitted a paper regarding this, regarding the error log collection and um, analysis and some software structure. So probably the next or sometimes later we can share what we publish it and what is our message through that.
That would be great. And one thing I would say is this isn't for academics, this is for industry people. But what we can do is
Yeah,
put your
yeah.
paper in as a reference.
Mm-hmm.
Right? So and we'll tie it together. Hey Anil, you have a comment?
Yeah, I just want to call out that there is another use case. I don't know whether we want to call that out here or not. When we do a manufacturing testing and screening out the bad DIMMs or bad memory, in that scenario, because we have very short limited time and we are running some control tests, so we do rely on just the count only.
Well,
And,
yeah,
and
I
basically,
mean, maybe.
the idea is that in the manufacturing phase, we don't allow any machine or component with any errors. That's the kind of nirvana, unless there is a need for it.
I don't want to, yeah, and this is really for systems running in the data center. And there are major differences. One of the major differences is that the diagnostic software controls what memory is doing. You are intentionally writing patterns to, and maybe not to the same place. And so the count is more significant because you're controlling the reads and writes. And I think it's more important here to talk about the kinds of things that happen while the system is in use, not while it's under test.
Right. As long as you make that clear, that the other use cases, detecting the persistent fault scenario. I mean,
I'm not sure I agree with your approach to counting, by the way. I'm just saying I don't want to address that scenario here.
I think it's, if I may, like Anil, I think that's a policy that you're talking about, not necessarily a way of diagnosing faults. And they're two separate things, right? Like, so this is
Oh, that's
how you
true.
would diagnose faults using patterns. But policy can be different from that. Like you may choose to discard a piece of hardware for X number of errors, but that's just policy. That doesn't mean that you've diagnosed the fault.
yeah, I mean, I'm just trying to say that there are other ways to diagnose. It's still diagnosed because we are taking the part out. Whenever we take the part out, right, from the production or from the manufacturing, there is some diagnosis involved, and that this is how we diagnose any if the error count reaches a certain limit, then we just assume that this part at the manufacturer itself has some anomaly, and we don't want to take it to the data center.
I'll tell you what, I'm going to put the system is deployed and running user workloads in as an assumption, and I want to ignore your scenario because I think that's a can of worms, and I don't want to get distracted. I want to talk. What I want to do is address something that most people care about, which is what are the misconceptions about tracking errors while the system's running? Because most
Exactly.
systems spend most of their time running user workloads,
Right.
and if they don't, then
That's
you're
all,
screwed up.
that's all I'm calling out. I'm just confine our discussion here specific
I
to the.
did. I've already done it. Sounds good.
Awesome. Thank you.
Yeah, I agree. Let's and then what we can do. I think your topic is worth coming back to. I'm not, but what I want to do is focus this so we get it out, and then what we may want to do is come back and say, okay, let's talk about best practices for kind of burn-in testing or or early life cycle fault detection. And then maybe that'll be a different discussion. Okay. And Roy, the other thing that you've done some work where you showed us we don't need to capture every error, and so I don't know how to refer to your work, but if we can, I would like to, I'm asserting getting a representative sample of errors is sufficient, and that has certainly been my experience and all my years of looking at memory errors. But you also did that study.
Mm-hmm.
If we could, is there some way we could reference because you presented it here. So for everyone else, I'm not giving away SK Hynix secrets. Roy presented something here a while ago. So, or if we could somehow like leverage or build upon what you learned in your study, that would be pretty awesome. But I don't know if SK Hynix is, wanting to publish that. So I defer to you.
Okay.
So if you could look into that or help us, I'll say, I'm gonna just say, I'll say, I think, oh, I'll just say, I don't know why I don't have your email. And if any other memory vendors have something, from your studies, that's great too. But I know Roy does because he's
Okay,
presented.
the one thing I want to add here is about the impact of the sampling frequency of the error logs.
Yes. Yes.
So,
Let me edit.
so Drew, can you scroll up a little bit? So, I mean, can we have a paragraph that says what is needed instead of what it don't rely on this, that, and that? Can we say to have a successful isolation, these are the basics data points that one would need?
Well,
Right.
that's kind of what the FMFM document is, right? So that's why I'm going to add the reference to FMFM doc.
Okay.
I'm not sure I understand.
Is this, maybe I'm not fully, so is this going to help guide the reader how to isolate, or is gonna guide to just the environment and how things work?
This is really just how things work, and if you look at the FMFM document, FMFM document says we want to gather this particular set of data for DDR5, and then we intend to build analyzers that use that data to infer the fault. In this case, I'm just explaining why we need analysis, and hey, don't count memory errors, and also please understand that software access patterns and patrol scrubber limitations play roles in. This is really to address misconceptions that people have, and then my ultimate goal is to point people to the FMFM document, and that's where we've agreed upon how memory analysis should work.
All right. Okay. Let's see how it pans out.
So, yeah, this is just a scenario. This isn't a specification. It's not a requirements document. It is supposed to be a narrative that walks through the progression of a memory error and clears up misconceptions about memory errors. That's all, and it's not even binding. It's just an example. And this is really kind of a little bit out of the ordinary, because usually say, what is it, a spec, a white paper, or whatever? But we need these scenarios because there's a lot of confusion about error handling, and there are only a few of us. Like half the world's error handling people are in this meeting, that work at this level. There just aren't that many of us that think this way, and so what I'm finding is I'm continuously needing to explain the same things over and over again. And what I'd like to do is write something with you all that explains it in a way that we agree and spreads our knowledge to a much broader group of people so that we can build up a bigger group of people that can do what we do.
This section, effective correctable memory error analysis rules. Maybe this is a good area for further elaborate on that, what is needed for that effectiveness, if you want to do that.
Yeah, and I think yeah, we can, like, I could have a section at the end and like summarize what an effective error analysis rule looks like. But I'll say effective approaches. But what I'm going to say is basically look at the FMFM document. And the goal is to map. So infer failure modes and assess risk of crash or launch. So it's infer failure modes from patterns. And I mean, that's that at a million feet is kind of the message of the FMFM doc, right? Is, you know, we're going to gather all this data, we're going to figure out what the pattern means, then we're going to see how good the ECC is and how much performance impact the problem occurs, and then decide what action to take. And, you know, if I have a, you know, a burst of 10 errors that just go away, maybe I say I had a soft error or something. You know, I might so you know, that all factors into the FMFM document, is that you know, one of our big goals there is to filter out soft errors. Okay, so we're about out of time. What I'd like to propose is, you know, just take a look, but please keep in mind this is just a walkthrough. This is not a set of requirements. And what I'm trying to do is show how the error grows in scope as memory uses, or as memory gets written to the non failed condition, and as software uses the affected memory more and more. So yeah, we'll just work on this, and I, you know, I think it needs to be clear, but it doesn't need to be perfect. But if you see anything that I really screwed up on, I'm happy to fix it. Okay. So, you know, and I guess a little feedback is, you know, are you all okay spending a few weeks going through this? I'd like to limit it to a few, you know, like 3 or 4 weeks at the most. But is this okay?
Yeah, Drew, I think this is a great idea, because this will help, you know, as you say, clear up misconceptions out there that we all kind of fight over and over and over and over again. And it would be great to point to this article to say, here, go read this, understand this. Then we can have a discussion of whether or not we should replace that memory.
Yeah. Well, and if I have your name on it, and Mita's and Roy's, and, you know, and Justin's, and, you know, Sean's, if we all have our names on it, when we, like, if we point our customers and partners to it, it becomes, it's not like, you know, a memory vendor speaking in their own interest. Look, Microsoft and Google may be here too. So it gives it a little bit more weight. The you know, hey, we agree there's a better way to do this.
Right. And if we get the DRAM vendors on the list also, which is in
Yeah.
their best interest too, right? Then
I hope so. Yes, this is really intended to be in the DRAM vendors' interests too.
Yeah.
Yeah.
Yeah. To clear up all these misconceptions and sending good DRAM back for FA.
We all win by getting this right. That's
Exactly.
Kind of
Yeah. Yeah.
cool. Okay. Well, please start editing. please add your name as you want, and even if you just read it, if you didn't agree with it, add your name. You know, like I would love more names on this. So I want this to be a something we all look at and go, yeah, I can point people in my company, I can point people to other outside my company too, and we'll kind of clarify how things work. So thank you, and thanks for your time today.
Can you also re-go through the share list?
I'm sorry.
Can you add the rest of us?
Oh,
I think I'm still waiting for something.
so I don't know how to add the whole group. Sean, can you get in?
Yeah.
Oh,
I cannot.
yeah. Okay. Give access. Okay, I am so sorry. Yes, I will. If I see people asking me for access, I will give it. So
thanks, Drew.
Okay, thank you. Thanks for pinging me for that. I may not have noticed that soon. And if please feel free to ping me if you can't get in or something and I'm not responding. I will gladly add you. Okay, thanks everyone.
Thank you. It's a
Thanks.
great job.
Thanks.
Bye.
That's great.
Talk to you later.
Bye.
Bye.
Drew, are you still there? Oh, that's true.